over to you.
So first of all, let me say I'm delighted to be here at this workshop and that we have finally got this workshop off the ground. Chetan and I have been talking about setting this up since 2018, I want to say, something like that. So it's taken a little while to make this happen, but we're finally here. And as Chetan said, we hope this will be an annual workshop that will be a good Asian Pacific sister to the Telluride and Kapokachia, the American and European versions of this workshop, effectively. So you're our guinea pigs. This is the first time we do this workshop here. In my experience, that also really can have an impact on the culture of the workshop, how the workshop operates and so on. If you've been to Telluride, if you've been to Kapokachia, similar topics, quite a different vibe, quite a different way these things work. I expect here it will be different again, and we have an opportunity to set that up. So for that, I would really like to thank all our speakers that have come for this very first one, because we really have an impact to influence this, but also you, the students. It's important that you give us feedback of what we should be doing here and what we should concentrate on, and at the end I hope we'll get some feedback as well of what we should concentrate on more or less. So I'd really like to thank you all and hope to have a very active participation at this workshop. Also like to thank the team that organizes it here at the Indian Institute of Science, and Chris for his ongoing support for neuromorphic engineering. That has also been going on here at the Indian Institute of Science since, I want to say 2017, something like that, a fair chunk of the time. And we look forward to growing this here in the Asia Pacific as well. So now let me start my talk. Today I'll be talking largely about neuromorphic systems and applications of that, particularly event-based vision, which is one of the topics that we'll be doing a workshop on here. It's a good talk, if I may say so myself. It's one that I've been given quite a bit in various versions over the last year and a half, including last year here at the Indian Institute of Science when we had a little workshop. It changes every time a little bit, but you might have seen some of the footage already. If so, I hope you enjoy seeing it again. If not, then my apologies, but I think there are lots of people here that haven't seen this work yet. So I'll talk about these now. So I'm talking about the research we do at the International Center for Neuromorphic Systems, which is the center I set up at Western Sydney University. I was the director up until the end of last year, up until 7 days ago, and have handed over the reins to Greg Cohen at the center to direct that now. At the International Center for Neuromorphic Systems, we try and do research in neuromorphic engineering in 3 different areas: sensors, then algorithms that take data from these sensors and processes that data, and then processors to run these algorithms on, so hardware platforms. And then you'll see in the top right, we're very much focused on making applications with neuromorphic engineering. I'll pick that up a bit in a moment. Now, normally when I give a talk, I'll explain a little bit still to people what neuromorphic engineering is. Since we're here at a neuromorphic engineering workshop and you've all applied to be at a neuromorphic engineering workshop, I think we can skip that part. But I do want to stress a part that there is an engineering side to it where we take inspiration from brains and neural systems in biology and try and apply it. And a science side of it as well that we shouldn't forget, where we're still so much to learn about brains. And so there's a serious neuroscience component to that as well. And again, hopefully they'll come out in this workshop. At our center, we have sort of a neuromorphic compute roadmap, and we need to watch a little. We'll get to that in a moment as well. Neuromorphic engineering and neuromorphic computing get used interchangeably, but they're not exactly the same in my view. But for the neuromorphic compute, at the moment, compute means sending a lot of data from our sensors to big data centers that are power hungry, often next to a lake to get the cooling as well, and next to a power center, a power generator that generates all the power. We're looking at making neuromorphic sensors, doing some local edge processing with neuromorphic algorithms. That's the type of work we're doing now in our center quite a lot of. That will then result in having to send less data to a traditional center, needs less storage, less compute power there, saves energy, saves bandwidth, saves data. And Chris, too, already mentioned in his speech, those are all issues that we're running into at the moment in the amount of energy that we use and how much data we collect and never do, which is why neuromorphic engineering has become so interesting to people. You can also do neuromorphic processing locally. This is often this step to go from digital edge processing to neuromorphic processing is either an academic exercise or an exercise you do by the time you really have a product where you really want to get to the lowest power possible for the product that you have. And then another thing that we're working on in Sydney that I won't talk about today, but ask me about it at this workshop if you want. We've put together a neuromorphic supercomputer that will be switched on hopefully at the end of this month. It will be the first neuromorphic supercomputer to do the same number of synaptic operations as a human brain per second. And so that will be hopefully a world first. And it's done with field programmable gate arrays, so reconfigurable hardware, commercial off-the-shelf hardware that everybody can buy, so people can make their own copies of this machine as well, which is different from, say, the aforementioned Low-E and True North, which is custom hardware with limited availability for people to make their own copies of these things. This is quite geared towards neuromorphic compute, which is taking data and interpreting it. In biology, actually, we don't have many brains that sit there and get a lot of data sent to them and then absorb the data and process it and then give you an answer when almost passively. The only example I can think of, and I woke up at 3 a.m. this morning, I was thinking about this, is students at school. Basically, they sit there often passively, receive their information, and then at exam time you have to give an answer to it. But that's the only brain that I'm aware of. Most brains in biology, they interact with their environment. And they're there for survival of the animal and procreation and finding food and not being eaten yourself, all those things. And that's the type of neuromorphic compute that these brains do, but it goes hand in hand with the neuromorphic sensing that their sensors do of these animals. For survival, it's look at your environment or sense your environment, interpret what you get in, perceive what's happening around you, and then make a decision and go take an action. Dragonfly, for instance, it'll see a mosquito that it wants to hunt. It'll make a decision to go after it. It has about a 94% success rate of catching a mosquito mid-flight. Now, if you've tried to do that yourself, you know that's difficult. It's very difficult to catch a mosquito. But they do this very well, and it's a task they need to do for survival because that's what they eat. Their power budget is about 20 mosquitoes a day, something like that. So that's about a grain of sugar, basically, all that computation. Now, I mentioned applications before, and I think this is important for us because I've been doing neuromorphic engineering for about 35 years now. And the first 25 years or so, it was a fairly small discipline that not that many people paid attention to worldwide. But over the last decade, it has massively grown. And with that comes a risk as well. And this is this Gartner hype cycle. I mean, they're not the ones that invented the hype cycle, but they've commercialized it or publicized it quite well. Let's put it that way. This is from 2017, so this is when we basically started talking about this workshop, maybe. And you'll see, I hope this is readable. It says neuromorphic hardware, brain-computer interface, edge computing, smart robots. These are all topics that we're looking at this workshop here. This is 2017. You'll see that these dots are colored dark blue, or brain-computer interfaces. They get a bit longer. That's the yellow triangles. Dark blue says 5 to 10 years to reach the plateau. That's to come here, come out of this hype cycle. So get all these people saying all these crazy things that it can do, and then realizing that it can't do everything, and a lot of the attention will go away. And then you reach a plateau where it just becomes an established technology that has products out. So neuromorphic hardware, this was 2017, July. So we're exactly 7.5 years, so we're exactly halfway in this 5 to 10 year time frame. So we should be having products there for neuromorphic hardware, according to this hype cycle, if we're an emerging technology. If you look at the 2024 emerging technology from Gartner, which I did, neuromorphic is not mentioned anymore. Now, either that is because they think we've already failed, or it's not an emerging technology anymore, according to them, right? After 5 to 7 years, we should be well into this slope of enlightenment, plateau of productivity area. We shouldn't be an emerging technology anymore in that sense. So, I'm worried that if we don't show applications of neuromorphic engineering, I mean real-world applications of products, let's call it that, of neuromorphic engineering, soon all this interest will go the same way as what happened to neural networks in the early 90s. Neural networks throughout the 80s was promising the moon and couldn't deliver because we didn't have the compute power to do it. But then there was a big crash in interest in neural networks, and it took up to about 2010 and the GPU maturation before that came back. So I'm hoping to try and avoid that a bit. So I'll put one, it happens to be my own, but one example of a successful product of neuromorphic engineering, and that has been quite successful. So this is a motion detecting silicon retina that I designed when I was working in Switzerland at the Swiss CSEM, Swiss Institute for Microelectronics and Micromechanics. Logitech came to us in 1992 or so, when laptops still had trackballs in them. Touchpad hadn't been invented yet. And they wanted, optical mice didn't really exist either much, except a SunSpark workstation version on a grid, for those of you that remember. So laptop either was a little joystick in the middle of your keyboard or a trackball, but the trackball had to be tiny. And the problem with that was that you have a high curvature on the ball, and you had these mechanical wheels that needed to touch the trackball to detect the motion in two directions, and they didn't work very well, basically. And Logitech said, well, can you make us a retina that just looks at the ball and tells us which way the ball is moving? We took inspiration from motion detection in the fly eye, correlating edges and changes across space and time. And that worked pretty well, this chip, and it came on the market in 1994 for Logitech in this format. Here as a trackball. 1994 was also when the touchpad was invented, so laptops very quickly lost trackballs, even though Logitech had planned for that, and they became all desktop trackballs in the end. A major advantage of a touchpad over a trackball is, for a laptop, much thinner. You don't need a ball, and your laptop minimum thickness is going to be the thickness of your ball plus a margin. Whereas with your touchpad, it's the minimum thickness of your touchpad plus a margin. So it's much neater. But the trackballs have been used. If you go to clean rooms, for instance, they often have trackballs in them rather than computer mice. Also because you need less space to move around the workstation, but also they generate less dust because they're not scraping on things. And so in this format here, they were produced up until last year. So last year they were discontinued finally. You can probably still buy them on eBay and so on, but they're not made anymore. But it was a 30-year runtime for a neuromorphic chip that was in technology that got used worldwide. And of course, pretty much nobody knows that it's neuromorphic technology. Once it's in there, it's just a device, it's a product that people have. But we need more of these things. So this is an area that we're very actively working on at our center, and particularly concentrate now on neuromorphic vision, which is where we're closest to applications. And it's in this area of perceiving the world, neuromorphic perception with electronic devices, that I think the first products will be made, rather than in computing. We can build neuromorphic computers like the Deep South supercomputer that we're building, but having that as a product and having that as with commercial applications, I think is many more years away than making smart devices that perceive their environment. If you think about how much your phone is perceiving about its environment these days, those are the type of tasks that we should be looking at. Okay, so we work with these event-based vision sensors. On the left is footage taken out of one of the university buildings with a standard phone camera, and next, at the same time, with an event-based camera. So the event-based camera detects changes, so where it gets darker or where it gets lighter. So local changes in contrast. Each pixel does that independently, and it will only tell you when a change happens. So when no change happens, you get no data from that pixel. And that's a massive data compression if you're looking at a scene where not much is changing, like this one. And you see on the right that, for instance, you can't see the buildings in this picture because the buildings aren't changing. You only see the things that move, people and cars. So if that's the thing that you're interested in, and usually that's the case when you're perceiving an environment, the static part, you don't have reminded of the static part every frame that you take. It's not that interesting. So where it gets brighter, we painted yellow. Where it gets darker, we painted blue, that event. And then we put a little temporal decay on it so that the yellow decays slowly to black over time exponentially, and the blue decays slowly back to black. That's done in post-processing just to make nicer images. That's not what the sensor does. The sensor just gives you the event when it happens. I got brighter. I got darker. So let me play this footage again now that we see it. Pay attention here for the cars going into the shadow, into the sun here. You can see the shadow that's being projected here by the sun appearing here, for instance, that you don't get before. But the cars themselves, they change very little in appearance. Because the pixels detect changes around their own range or own level, they have a large dynamic range and are quite insensitive to in-frame changes in background illumination. So we can slow this down, and if we do this with standard footage, of course it gets jumpy because we're only recording a certain number of frames per second, whereas it gets still very smooth with the cars. You can also see additional things like the raindrops falling. It's raining here, and if you go search in this, you can see people with an umbrella and work out that it's raining, but it's much harder to see. You can't see the actual rain. There's also, let me play this again, some other things that we see, birds. There's some cars down here because there's a street here that you don't realize that it'll pick up. So I think that's a car going down there. The people moving. So to drive that home, the difference between the two systems is, on the left, the video is just a stack of photos. And on the right, this event-based sensing is a XYT cube of data, a space-time cube of data. You get, this happens at this point in time, this position in X, this position in Y, and that's what the data is made of, at very high temporal resolutions. Like the sensor itself just detects when the change happens, but then in order to get it on a computer, you timestamp it, and we timestamp it with a microsecond resolution. So I'm talking about the high dynamic range. This is the sun that this drone just flew through. So you can see we can stare straight into the sun. This is a tree here, and you can see the shadow and the sun glinting off the tree. It's a bit down the bottom corner. But you couldn't do that with a standard camera. Look straight into the sun, still see much of the tree because everything else would be underexposed. If we look at this in a bit more detail with this drone, for instance, so this is the sensor's field of view. This is a zoom in, but this is what it actually is seeing. And we're tracking some features that we learn at various parts in space. And this is still the sun, so this rotor is in the sun. But from this, we can work out how fast these rotors are spinning, how many rounds per minute each of these rotors is doing. And once you do that, and you have a model of the drone, and this is like a DJI drone or something that there exist quite good models for. If you know how the rotors are spinning, you can start predicting how it's going to move, because it needs to change its rotor speed before it moves. Now, here it's fairly trivial because we have a very good view of a drone. If you wanted to do this, say in the Ukraine at the moment with drones coming at you, if they're that close, you're probably too late to do anything about it, right? You would want to see that a bit further away. So here's an example of where we do it with an octocopter at a few kilometers away with zoom optics. So here's an optocopter drone in a distance. This is taken from a standard camera. This is the zoomed in view. This is actual what you're seeing with the sensor. Here we're learning features, and we're learning a separate set of features for each of these rotors. And that's self-supervised learning. And these features, they're in competition, and as you can see, they're sort of the different angles of the rotor that you learn. And so then here, for each of these rotors, we're labeling which feature is the most active at each point in time. And that gives you a very nice periodic signal, even though the features become the vision becomes very small, and it's maybe only a few pixels across still, what you're looking at. And from this periodic signal, you can then extract still how many rounds per minute each rotor is doing. We've also done this on a moving platform. So previously it was all from a stationary platform, so nothing else is moving. Here we're on a boat, and we're looking across the water, and this is the original footage. This is stabilized by detecting the horizon and stabilizing the horizon. You see the waves here too. The native DVS, or the event-based data that we get, has this wavy pattern in it, because the waves themselves create additional events every time we move more, right? Because the background moves more. So we're tracking a drone, we're discarding birds and insects and so on that are going through the field of view at the same time. And again, this is a couple of K across a bay that this is done, and that we can track these drones with this. So that's one area we're applying this. Yes?
The previous ones, all the images that you've shown us, the structure in salmon, are these all denoised and reprocessed?
You mean the standard footage, or?
This is not the still one, but the still one, did you actually denoise them because they look pretty clean?
No, they're not denoised. They're just a good event-based camera. They're the Prophecy Gen 4 made by Sony HD camera, which is the lowest noise and highest resolution one that you can buy at the moment. That's raw data, yeah. So another area that we've been playing with is rocket launches, to look at that. You need to have something that can operate very fast. You have a very high dynamic range of light intensity that happens when this thing ignites. On the right is quite a good Sony video camera. You can see its auto exposure can't really cope with the ignition of the rocket. Whereas on the left, you can see some artifacts from the ignition, but you can see a lot of details in the exhaust, things flying off, spin rockets kicking in to give the sounding rocket its stabilization spin, things like that. On the right, the Sony is just recovered, but the thing has left the field of view, so you can't see anything anymore. So this is a good use case for a camera like this. This is just at the moment of ignition, but normally with rocket launches, you can't actually get close to the launch facility in many hours before, and sometimes things get delayed as well. What we do with this is we just let it run. And down the bottom we plot the event rate we get from the camera, and in this case it's just the stars moving, so the event rate is pretty stable. Here we have a shooting star, which is why we slowed down the footage, but generally when the event rate is stable we just don't care too much, so we can speed this up. And it goes up to like 5 minutes per second basically that we're doing. You see some clouds coming through that create some waves in the events that we have here. The stars are moving, well, the Earth is rotating, the stars aren't actually moving, they're the stable frame of reference. And then here you can see a change in the event rate. So we're going to slow it down. We know something is going to happen here that we might want to look. And we can even go to like a quarter real time, I think we do here. Yeah. And we're vibrating quite a lot too. We're so close that the camera, the whole system is vibrating from the rocket launch. And then we get washed over by smoke as well and things like that. So the rocket is still going here, but at the moment it will switch off. Here, everything goes off events. The light's gone. That we get some smoke washes over us that reflects some local light, and then the second state ignites and the rocket goes off. So those are some use cases. They're not really applications yet in that we're not making a product with that. Where we have is with this one, our AstroSite. We've created a startup company, a spin-out from the university called Optera. It's doing space domain awareness with these cameras. So you take these cameras and stick them on the back of a telescope to look at the night sky and track satellites and space junk. Why? Well, if you look at how many objects there are in space, this has been really more than exponentially growing over the last few years. A large part due to SpaceX, and Starlink satellites that are going up, but also due to some satellites being destroyed, one by India, I believe, which created a lot of additional space junk, and that is floating around. So you see these massive peaks here. These discontinuous changes are satellites that have exploded. And there is a risk there that if we get so much junk in space that it hits another satellite, it's called the Kessler effect, and it's a snowball effect. It hits a satellite, that satellite disintegrates, now you have more junk. It hits something else, and there's a risk that we will lose our space infrastructure. And if you imagine how much of everything that we do these days depends on our space infrastructure, it'd be quite catastrophic. You wouldn't be able to pay with your phone anymore, you wouldn't be able to send messages worldwide anymore. The internet would go down, navigation would go down. Well, they're in slightly different orbits, so not everything might go down at the same time, but it's quite a serious, it would have quite serious consequences if that went wrong. And when we started looking at this, I mistakenly assumed satellites are like planets and stars. Once you know where they are in the night sky, you can predict where they are going to be for millennia. That's not true for satellites. Satellites are still, particularly the low Earth orbit ones, they still are in a little bit of atmosphere from the Earth, but all of them, they're also subject to solar winds, for instance. And they're in other gravitational effects and so on. So their orbits aren't as predictable as you might think. And actually, an orbit is only good for about 24 hours for many of these, if you want to be on the safe side. And being on the safe side means with a telescope, you're effectively looking with a straw, or through a straw at the sky. And so you're only seeing a very small part of the night sky. If you don't know where to look for the thing, it's going to be very hard to find it again, searching with that straw. So you want to be that accurate that every time it might have moved a little bit, but it still needs to be in the field of view of that straw. And that's why it's so important to get eyes on multiple times a day of pretty much every satellite that is out there. Now, traditionally, optically, this is done like this, where you take a 1 second long exposure. That's why all the stars that are moving up create these little streaks, because they move that far during the 1 second. And you do that every 5 seconds. And then you try and figure out what isn't a star in there, what is different. It's very difficult to do here. Here we're actually tracking a satellite. Well, it's not us doing it. A satellite is being tracked in this image. So this is the first participation question here of the workshop. Can you spot the satellite in this?
So you already read the frame?
No. It is there. We're tracking it. So that should be a giveaway. If you're tracking it, where should it be? So,
exactly in the middle, right?
Yeah. 1,000, 1,000 there. That one. I mean, so it's very hard to see. And I mean, if you know it, then it's a little bit easier. But there's a trick here. If I do this, now you see it, right? As a stationary point and everything else is moving. So it's this jiggling it back and forth and speeding up time with these things. Because it's the way we're doing it like this, we're looking at individual photos and then we're trying to correlate across photos. That's not what our biological vision system is made for. If we turn it into a movie with stationary objects and moving objects at the right sort of speeds that our visual system is good for, then that works much better. To do these sorts of exposures, this is done generally in astronomical observatories. They're on top of mountains so that they got good clear skies, in dark areas so that there's less light pollution. And it's often like granite mountain, concrete slab, big building, massive setup, everything to stabilize it as much as you can so that you can hold things very still because you're exposing for a second. And you don't want that satellite to move for that second. So you need to track it accurately. Or you could do it the other way around and track stars and keep them all still in the field of view and see the satellites move. But now you're not integrating the satellite light on 1 pixel. So you're going to need more light from the satellite in order to do that. Was there a question? Did you have a question?
I just wanted to ask, is this satellite stationary or it is moving much slowly compared to the Earth's rotation?
Yeah, I'll repeat the question. So whether this satellite is a geostationary satellite or another orbit, depending on how it's moving and so on. Looking at how much the stars move during 1 second of exposure, so in fact how much the satellite moves relative to the stars in 1 second, this is a geosatellite. But I don't know, I just have this footage, I don't actually know what they're tracking here. But this would be a geostationary satellite. And that brings me to a good point. There are sort of 3 main orbits for satellites that are used. The low Earth orbit satellites that are about 400 kilometers high in space, so they're actually quite close. 400 kilometers is not that far. You have the geostationary satellites that are 36,000 kilometers away in that area, because that's where the point is where you can stay stationary over a particular part of the Earth. They're actually doing little figures of 8 typically. They're not perfectly stationary. And then in the middle is sort of 18,000 kilometers, 16,000 is where our GPS satellites and a bunch of others are operating, medium Earth orbit satellites. So we've Instead, because with these sensors, we don't want to keep things stationary in the field of view. It's an event-based sensor. If you keep something in the field of view and it's not changing, you get no events from it. So we don't need to be as still. We actually want things to change. Now, from the ground, looking at stars or satellites, they're never perfectly still in the field of view, partly because of atmospheric aberration that gets you the twinkling of the stars, effectively. So you constantly will get changes, but not as much as when they all move a little bit. So we don't need such a stable base to operate from. And so we decided to do it differently with these sensors. And we put them on telescopes that can be remote controlled in shipping containers. And with a sliding roof, telescope comes out, as you can see here at the bottom. We now have a third one of these, so we now have 3 of these. And we can place them anywhere. And the good thing about shipping containers is there's a whole industry that moves shipping containers around the world. So it's very easy to take shipping containers. It's also for if you're monitoring your own intelligence satellites, for instance, and you want to know if there's an adversary moving a satellite near yours or so, or changing it. They will know where to do it, at what point in the Earth you have the least visibility of something, because they know where all the big telescopes are and so on. But if you can put shipping containers that could be telescopes anywhere around the world, now you can't play that trick anymore. So it has those sorts of advantages. We can ship it in, like on a standard shipping container truck that moves it. Here we moved it to the South Australian desert. This is a site where we've been operating from for several years now. It's desert. You can see as soon as you put an optical telescope there, it starts raining. It's just one of those facts of life, but it dried up pretty quickly. But if it doesn't work out for this company, we can always try and sell it as a rainmaker around the world. But we bring it in, we then just, you see the site, it's quite remote, it's clear around, dark around. In the back there's all these solar panels as well, so it's off-grid, it can operate. It was cloudy, it rained, but then luckily for the night it cleared up, and we just need this clear night, and the satellite starts calibrating, or the telescope, our astrosite, starts calibrating itself. It just needs an hour or so to figure out from known stars and so on and correlations, building a model of how it's pointing and where it's looking, and then it's ready to run. And then we can run this remotely, so this is massively sped up, but we can set it as a schedule of observations, go look at these satellites, do the recordings, and then at the end of the night pack yourself up. And we've been doing this routinely throughout last year because we had a trial with UK Space Command that was running both the one in Australia, and we shipped one of these shipping containers from Australia to the UK to use there. You think that would be easy to ship a shipping container. It was actually way harder because it's a modified shipping container than we ever thought. But we did it, and we had a successful trial in the UK to do this, starting in March last year. Now, March doesn't seem like the best time in the UK to start looking at the night sky, but it worked out reasonably well still. And so we have recordings of these satellites, and it's typically like 700 recordings per astrosite per night that we're doing with these, of objects. And what we then do is we get, say here, the event-based footage that we get. We automatically extract everything that moves together. That's the stars. And then what's moving differently in here, that is an object of interest, a satellite or space junk. And so we can localize this now relative to the frame of reference that the stars give. Because what we do is we match the pattern of the stars against the database. It's very well known, the database of stars. So we can get a reference of the stars, and the stars, each known star has coordinates, and right angle and declination is the coordinate system. And so we can then give this with a microsecond precision locations in right angle and declination once we've extracted that automatically. We take this footage, we automatically extract that, we separate things out automatically. So here I'm plotting the events of the object that we were tracking in colors. Here, this is the stabilized star map. The octagons are the stars in the database. The numbers are the known brightness of these stars according to the database, and the matching that we have. And this is the object that we were tracking, and we're coloring the events as time as a color, just so basically you get a sense of which direction this is moving into. This is early, this is late, so this one was moving in that direction. But also what we can do is we can plot the event rate, not of the whole camera, but just of these events that we get from this object across time. And here you can see that this has this clear periodic signal of about 5 seconds per period. So this object is tumbling at one rotation per 5 seconds, or maybe it's half a rotation per 5 seconds, and the sun is glinting more or less of it depending on the orientation of the satellite, and that's giving us the light that we're detecting. So apart from telling where it is with good precision, we can also start saying things that you wouldn't see if you're integrating, or if you're only taking one 1 second exposure every 5 seconds, you wouldn't be seeing this. So those are some of the advantages of that, and hopefully we can, this year we can start selling these astrocytes as a proper product of neuromorphic engineering. Second example, again, it's more of a use case than a product, but it's an application nonetheless. We have 2 of these sensors on the International Space Station at the moment. They've been running for almost 3 years now. In end of the month, it'll be 3 years that have been up and running. It was meant to be a 12-month science project, but the data that we got was so interesting. This is a collaboration with the US Air Force Academy, and therefore partly funded by the US Air Force and with NASA. And the US Air Force was quite interested in the data that they're getting from the sensors. So instead of letting it run for 12 months, they left it for 2.5 years on the space station, and then they really needed the spot that the sensor was at for another project, which was on the Columbus module that the sensor was at. So they took the sensor on. The normal procedure then is to jettison it into the upper atmosphere so that it burns up. You're not getting your package back from them. But instead they've moved it to the other side of the space station, and now we're actually, instead of looking down at the ground, we're looking out into space and getting other data from that sensor. So when we're looking down at the ground, here's an example. This is a high definition, high resolution standard camera taking an image from the International Space Station. This is what we rendered from our sensor. What this sensor is doing, it's because this was the first time we sent anything to space, we sent the best known, oldest version of the sensor that we've been working with to space, which was one made by Toby Delbrook, who will be here later this week. It's only 240 by 180 pixels, so it's a very low resolution sensor. But what it's doing, it's effectively a scanner, like your old photocopier scanner or document scanner, in the direction that it's moving, because it's responding to changes with quite a high time resolution. So you can actually build up quite a high resolution image in that direction. In the cross direction, you're stuck with whatever resolution you've given it. Unless you start jiggling the thing sideways, which I guess you could build a system that tries and does that as well. So basically, as the ISS goes around the Earth, it goes over, like, it just makes this long apple peel basically of an image that we're observing. Here we're rendering one that was done over Cairo, for instance, in the Suez Canal. This was done at night. The previous one was done during the day. During the day you will see clouds and so on. At night you mostly see lights, things that have lights on them. But that includes container ships and things like that, lighthouses, highways, and urban centers, as you see in here. The other camera that we have, it looks at the horizon, and for the first almost a year or so, it wasn't really, well, it was switched on, but we weren't really looking at the data because we were too busy with the data, looking at the ground and seeing what we could get from that. And then when we did start looking at it, we went, That's disappointing. This is just noise. We're not getting anything. There's no denoising in this one to answer your previous question. You could go, oh, maybe here there was something here. Let me just go back here. At first you see nothing, but then you go like, oh, maybe something is crawling down here. There's some structure in here and so on. Anyway, if you do the same trick that I did with the satellite tracking with the standard camera footage, and we take this and we speed this up, we jiggle this a bit faster so things move at a speed that we detect a bit more, and do the trick where we give it some exponential decay in event when it happens, so you have a bit of an after effect of every event, so you can more easily correlate things across time. You get this, same footage, still no denoising or anything, and now you can start seeing things. You can see these are features on Earth, probably cities. The things going up, they're stars, because that's the direction the ISS is rotating in, so the stars are going up in that direction. And then, hey, something here is moving differently. And then the longer you look, you can go, oh, maybe there's another one. And the more you look, you can identify more things. So if we extract the stars, again, we have enough stars here to give us a frame of reference, right angle declination, so we can fit things into that. We can extract other things that are moving differently from that, and they're all satellites. In fact, there's another one somewhere up here that we miss in this footage because it's actually just cut up at the top. And so we can extract all these, and so when we overlay this on a nice image again, we can work out, okay, so these features that we were seeing were indeed cities, so we're near Harbin in northern China, and these are the satellites that we were seeing, and of course because of the orbit that the ISS is in and looking at when you're looking straight ahead, so it's 400 kilometers high, it's pretty much all Starlink satellites. Not all of them, there's one that wasn't. We're labeling here the distance to the satellites as well, to each satellite. That's extracted from the known position of the space station and the database of the satellites. That's not something we're measuring, so that's a little misleading, so that's a disclaimer. So none of these things, looking at the ground and extracting features from the ground, looking at stars and satellites, was the original reason that this went up. The original reason was to monitor lightning, but in particular what are called sprites. Air Force Academy in the US, there's a researcher there. He's very interested in these sprites that are forms of lightning that go from the clouds to the upper atmosphere. So most lightning is cloud to cloud, then you get cloud to ground, and then sometimes you get cloud to upper atmosphere discharges as well. And they're hard to study from the ground because they're typically above the clouds, you can't see them, you don't know when to look. They've done some high-speed recordings with like high-speed video cameras and aeroplanes to try and fly by. But you have to fly near a storm at the right time, trigger the camera at the right time. Those cameras, when they record, they can record for like 3 seconds, and then their terabyte hard disk or memory is full, and then you need to get the data off. So it's hard to do active recording. So it was thought that this was a good application. You can deal with a high change in dynamic range, they're fast, and you can detect things. The downside with this old camera that we've sent up is we have no resolution, and you can't play the same trick of trading off time for resolution because lightning is lightning fast. It doesn't last very long. So you don't have much time to trade off. So you need better resolution to do that. We can show that we can see it. You might also notice if you look at it here, there are some stars here that we see moving up and down. Again, we're jiggling this back and forth so we can see that. I haven't been able to spot satellites in here by just looking. There might be some, don't know. But we now have a follow-on mission because of this to put these prophecy fourth generation sensors up. The launch, Alex, is it still March or is it now pushed to April? April. So I mean, yeah, it might be pushed again because this is the third or fourth time it's been pushed by a month. But the next version of these sensors should be going up in April this year, and they will have much better resolution and be much less noisy. So if you look with one of these good sensors at lightning, again you can see the rain coming down very heavily. This is just taken out of our lab. You can slow this down quite a lot, and it becomes quite matrixy with these raindrops going down nice and slow. But you can see the light, and you can really start tracking how this lightning develops and where it lights up and where it goes dark again. You do get some artifacts from just saturating the bus on how many events you can get off the chip. But you can do really nice observations of lightning with these sensors. You can even slow this down to like the equivalent of 1 million frames a second camera, and lightning gets boring effectively. It's like you can see the tendrils grow, but it's very slow to look at. So you can really capture these fast events with this. Alex at the sister workshop or mother workshop, however you want to look at it, at Telluride, this last year, did some recordings where we had 3 event-based cameras to try and observe the same lightning strike from 3 different positions. Here we're showing 2, one from San Sofia Mountain and one from Mountain Village. The third one we didn't show because it was almost struck by the lightning, as I believe. It was like right under it, so it didn't actually have it in its field of view that we got. Once you have these different operations and the cameras are time synchronized, so these were synchronized with GPS time, then you can start correlating the events from multiple directions, and you can sort of do a 3D reconstruction of the lightning and where it struck. So now you can start tracking these really fast events that are bright. You can imagine that this is lightning coming down, but it could also be rockets going up, for instance, that you would be tracking with this sort of data. So as I said, the new version is going up. It's like these are now to scale to each other at least. This package, the new package, is about sort of like a large shoebox. It has steerable mirrors in it. It has zoomable optics in it. This one, as I said, in the cross direction, we couldn't do anything about increasing resolution. And the resolution is around 250, 300 meters per pixel on the ground from the ISS. With this one, this should go to about 7 meters per pixel on the ground when we zoom in. But you can also zoom out to have a larger field of view, and we can steer the direction of the field of view. Whereas here it's all fixed. We'd have to move the whole International Space Station to change the field of view, and they don't let us do that very often. Getting it in space, I mean, it's one of the coolest things we've ever done, frankly. They're great projects. It's also very expensive getting stuff into space. So one of the things that we've started working on more recently is high altitude balloon flights in the last year. So there you can go up to sort of 30 kilometers height. It's not quite 400 kilometers, but you're already in the dark sky part of the atmosphere, for instance. So the sky turns dark if you go high enough, and you can start, and you're starting to increase solar radiation that your components are getting and things like that. So you can do tests, and it'll cost you maybe a couple of K to do a test for a day. You know, it's not that expensive. So we can do many more of these, can try many more different things out. As I said, you have dark sky conditions, 5,000 to 10,000 times higher radiation that we have, and you don't have to worry about clouds anymore once you get to those altitudes as well. So we're learning this at the moment on how to do this, and we've done a number of experiments. Here we're with a GoPro. This was heated. We had another GoPro on there, and we realized that there is a part where it just gets too cold in the atmosphere and the GoPro freezes and you get nothing off it. This one was heated. You can see it's not very well stabilized, the image from the balloon. And then I don't know whether no, it doesn't have the popping on it. And here, this is the event-based camera from the same. It's a little hard to see, hopefully you can, and this is when the balloon pops. So now it starts to go in free fall. Okay, so you get a lot of events from the sensor, and occasionally you see the sun and the moon in the field of view as well. But the sensor still keeps responding even at this speed. We can't see anything at this speed, but we can slow this right down as we've done before. This does not stabilize the image, but slow it down so that we can still see the ground features and atmospheric features where you see multiple lines of refraction in the atmosphere, and if the camera moves in one direction, they get brighter, so they go yellow. If the camera moves in the other direction, they go blue. And so even when it's spinning that much out of control, we can still get data off it. Obviously, we'd like to not be that much out of control and be in control of what we're doing when we're doing this. So it's about getting these up there. Another plan is to introduce gliders under the balloon and the camera on the glider, so that when the balloon pops, the glider can keep the camera up there for longer, so you can do these experiments for longer and under a more controlled environment. Finally, here a plug. I realize this is always the wrong audience, but you never know who might know somebody who might know somebody who is interested. So we've introduced the world's first Masters of Neuromorphic Engineering that you can study with us at Western Sydney University. It's a 2-year degree or a 1.5-year degree, depending on how you choose it. For both, the first year is coursework, 4 units or 4 subjects per semester, 2 semesters. And then if you want to go into industry, maybe do a half-year research project, maybe with an industry partner, and then get a job. If you want to go on and do a PhD, then do the full year a project for the master's degree, or if you want to qualify, so that allows you to qualify for entry into a PhD program into Australia if you've done the 2 years with this large research component. And it also qualifies people for a visa in Australia, which is why a 2-year program is quite important as well. And for instance, this year we will have some students being sent to us for the first time by the Indian Armed Forces. So we'll have 2 cadets from Air Force and 1 from Army starting with us this year, and that's meant to be an ongoing plan as well. And we seem to be having much more luck with this program, attracting candidates who want to increase their education. They already have a job, but they want to specialize within their job, and their employer wants them to specialize in their job, and their employer is sending them to us, as opposed to students that enroll directly from undergrad into this. But so please, if you know people that want to learn how to do all these cool applications, then here's a way to come and learn it from us. And with that, I'm open for questions. Thank you very much.